Okay, so I'll start now. So today we'll be learning about 2D motion. So first, I'll go over vectors and scalars for review. So in physics, there are two kind of quantities. There are vectors and scalar quantities. And a scalar only has magnitude, while vectors have direction and magnitude. So as you can see in this diagram, um, for example, distance, speed, mass, energy, density, and power all are scalars because they don't rely on direction or anything like that. And it just relies on magnitude. But for example, vectors, such as displacement, velocity, acceleration, force, have magnitude and direction. So for example, if something is going this like 10 meters and then going back 6 meters, then the scalar quantity for that would be distance. So it would be just 10 plus 6 equals 16 meters. But the displacement for that would only be 4 meters because since it's going 10 meters to the right and then going back 6 meters, it would be 10 minus 6. So it would just be 4 meters for displacement. So that's a review of those things. So then I'll next be talking about vector addition. So vectors need to be added and subtracted a certain way because they have directions. So there are two ways to add vectors, the tail to tip method and the parallelogram method. So as you can see in the diagram, if I have a vector like this, u, and also a vector like this, v, um, then you would first have the first vector, which is this is the tail and this is the tip, and then connect the head of the first vector to the tail of the second vector. So this is u, then this would be v. So as you can see, I'm connecting the head of the first vector to the tail of the next vector. And then the sum of them would just be from the tail of the first vector to the head of the second vector. So this would be u plus v. So that's the first way to find the addition of vectors. The second way would be to use the parallelogram method. So it says place both vectors u and v at the same initial point. So if I have these two vectors and I place them both here, so u would go like this and v would go this way. So it would be like this. So now that you have these two, you can put them in, you can draw the rest of the parallelogram. So it would be like this. And then the sum of that would just be the diagonal from this point to this point. So this would just be u plus v, this one right here. So those are two methods to find addition of vectors. So now I'll be talking about subtraction of vectors. So vector subtraction is basically the same thing as vector addition, but now you have, for example, if you have v minus or u, then you wouldn't want to write it like this at first. You would want to write it as v plus minus u, because this is just writing it as addition vector. And then if it's, for example, u in this diagram would be like, let's say v is like this, and that u is initially like this, then negative u would just be going the opposite direction. So you can use the same methods, the tail to tip method, and also the parallelogram method. So in this diagram, you can see they're using the parallelogram method. So if I draw them both at the same point again, this would be v. And since he's going this way, this would be u. So negative u right here. And if you draw the parallelogram again, it would just be like this. So this diagonal would just be u plus negative v plus negative u. or just u minus v. And another example could be if you have a vector like this, v1, v, and then this is u. So if you're trying to find v minus u again, it would be, this would be still v, and then u would just be like this. This would be a negative u. So I'll figure this stuff. Then, so I'll draw it again. So this is v, and then this would be negative u. So if you're trying to use the tail of the tip method instead, then you would still do the same. So if I have negative u like this, then I would connect this vector to the tail of this vector. So it'd be like this for v. And then this sum would just be from this tail to this head. So it'd be that. So that would be v plus minus u, or just v minus u. So those are two ways for doing subtraction as well. Okay, so now I'll talk about vector components. So if you have, for example, a coordinate system like this, with this being the positive y and this being the positive x. Oh, sorry, positive x. And this is the origin. Then, for example, let's say I have a vector going like that, vector v. So now since it's in two plane, in xy plane, there would be a component here, just the x component, and this is the y component. So this is vx, and then this is vy. And it's going at this at an angle of theta. So if you guys already know some basic trigonometry, you should know that if you're writing the equation to find vy and vx, and you know theta and v, then it would just be sine theta, which would just be opposite over the hypotenuse. So sine theta is equal to vy over v. And then you have that cosine theta, which is adjacent over hypotenuse, which is vx over v. So vx over v. So you can use these two equations to find that vx, for example, in this one is equal to v times cosine theta, and that vy is equal to v sine theta. So that's how you find the components of a vector, but some other important equations could be like, to find v, how do you find v? You would just use Pythagorean theorem, which would just be v squared is equal to vx squared plus vy squared. So v would just be equal to the square root of vx squared plus vy squared. And if you're trying to find the angle now instead, then if you guys may or may not know tangent as well, so tangent theta is equal to, so it'd be opposite over adjacent. So vy is opposite and adjacent is vx. So vy over vx. So to find the theta, then you just need arctangent. So you guys might not know as well, but it's arctangent of the value of vy over vx. So that's how you would find theta as well. It's important to realize as well that depending on, like, for example, if I had a vector like going down like this, and this is theta, then this is v, then it's not always going to be v equals v, vx is equal to v cosine theta and vy is equal to v sine theta. This y would be negative because it's going in the negative y direction, and the x would still be going positive. So it's important to draw it out first, and then know where the negative and positive are, because this would be negative v sine theta now, and this would still be v cosine theta. Okay, so now that we know that, I'll give you the first example question to do about vector components. By the way, do you guys understand the vector components? You can just write in chat if you do. So in this example 1, it says a mail carrier leaves the post office and drives 22.0 kilometers in the northern direction. So if we make this coordinate system again, this is the positive x, this is the positive y, and 22 kilometers in the north. So starting here, A goes 22 kilometers. And then to the next town. And then she drives in a direction 60 degrees south of east for 47 kilometers to another town. So that would just be like going southeast. So that would be going this way. So this is, and then when it says 60 degrees south of east, it's not this angle right here. It has to be this angle, 60 degrees from this angle. And this would be 47.0 kilometers. This is also kilometers to another town. So what is her displacement from the post office? So her displacement would just be from the starting point to the final point. This would be her displacement d. So what is her displacement? So you would need to find the components of d, or the x and y components, and then use d equal, and then use Pythagorean theorem, d equals dy squared plus dx squared. So I'll give you guys a few, like 2 to 3 minutes to try that. And you have any questions or you have the solution, then just message it to me in private chat. Okay, so I'll just give you guys 2 to 3 minutes now. All right, so I'll begin to explain it now. So basically, the you have to find the components of this D right here. So um to do these kind of questions, it's best to just list out the components of each vector you have. So for this, we're gonna say V1. We're gonna V1. We're gonna say it's V1x and V1y. So the V1 for this vector y, you can see that's only going north. So there's zero component for the x and 22.0 kilometers further north for the y direction. So that's for our first vector. And for our second vector, it's different because this one has x and y component. So you can see that equals, so if we draw this out right here, so it would be like that. So this is 60 degrees and this is 47 kilometers. So this is our Vx and Vy. So like I was talking about before, you always have to draw them out and find each component because like in this example, V2x would be equal to cosine 60 times V times 47. So 47 cosine 60, except the y, since it's going downwards, it would be V2y would equal negative 47 times sine 60. So these are your two vectors that you have. So now to find the components of the last vector, you would need to add these components, the two x components, and add the two y components. So for Vx of this vector, it would equal 0 plus 47 cosine 60. And then for the y component, it would be Vy is equal to 22 and then minus 47 so 47 sine 60. So I have the exact numbers for these. So this one would be 23.5 kilometers. And this is in the positive direction. And this one would be negative 18.7 kilometers in the negative y direction. So now that we know that, we can write that v or d, it can be either way, is equal to the square root of vx squared plus vy squared. So that we found right here. So it would be equal to 23.5 squared plus negative 18.7 squared. And that would be equal to 30 kilometers. Okay, so now if we go even further and try to find, for example, the angle that this angle right here. So if I do like for this D, we found it and then find this angle, it would be dy over dx. So then we would get that tangent of theta is equal to dy over dx. So we found that as negative 18.7 over 23.5 kilometers. So we find the arctangent of this. So theta is equal to arctangent of negative 18.7 over 23.5. Then that would equal negative 38.5 degrees. And that makes sense because your angle is going downwards. Like that, your angle is going down. Okay, so you guys understand this question? Okay, so now I'll give a review of the kinematic equations that you probably learned in week 1 of this club. So the first kinematic equation is in this diagram right here is the final velocity is equal to the initial velocity plus at, with a being constant. And the second one is the change in the x, which is x final minus x initial, or delta x, is equal to final velocity plus initial velocity divided by 2 times the time. And then the third one would be delta x, or the change in x, xf minus xi, or xf equals xi plus the initial t plus 1/2 a t squared. And then finally, the fourth equation is just the final velocity squared is equal to the initial velocity squared plus 2a, and then times the change in distance. And these equations also apply in the y direction as well. So instead of this being xf minus xi, it would be the final position in the y direction minus yi. So for this, it would look like, for example, this is the initial point and this is the final. So this would just be delta x, but for y, it would be this initial point, this is the final point, or this initial point is the final point. So yf, yi, and this is delta y instead. So it would be the same equation, but you just change all the x's, delta x, delta x, delta x with delta y. Okay, so now I'll actually start talking about what projectile motion is. So projectile motion is just 2D kinematics. So as you can see in this diagram, which I'll draw out here as well, you can see that this is the starting point. They made this the positive y, this positive x, and you launch a projectile like this at initial speed v, and it goes like that. So it ends here, but let's pretend it also goes like final. So if I make this my v initial, then this would be my vx, which is my initial x component, and this is my initial y component. So you can see in the diagram that this is theta. So the v component in the x direction is always going to be constant, like the same, wherever it is on the projectile. But the y component is changing from, it's like going like this, and then at the top it's 0, and then it's going down like after. So there's also this cool site which has a simulation of projectile motion that I would like you to I'd like you to see. So another thing in this projectile motion questions is that we're assuming that there's no air resistance or anything like that. So it doesn't matter what the mass of the object is when you're shooting it. It's just going to be some random particle because there's no air resistance. So it wouldn't make a difference in the projectile motion. So as you can see in this simulator, you're able to change the height of this projectile, and you can shoot it at different angles. And you're able to launch different things such as cannonballs, humans, pianos, and cars. And you can see that if I just have a random height and I'll launch at 0 degrees, then if I'm shooting a pumpkin, it lands there. And if I'm shooting something like the piano, it still would land in the same position because there's no air resistance. But if you turn air resistance on, for example, then the piano doesn't go as far. And if you shoot a cannonball, or let's say a pumpkin again, then the pumpkin would go, if you can see closely, that's like not the same distance they went. So you're also able to show the components. Reset. So you can show the components of the vectors. So for example, if I shoot it, you can see that the X component is always going to be the same. So if I make it slower, you can see that the Y component is decreasing, and at this point, at its max height, it becomes 0, and then it starts going in the negative direction. But this entire time, the X component is always the same. So I'll post this link in the chat for you guys. Yeah, you guys can play around with that after this class or during this class if you want as well, I guess. But it's a fun way to understand projectile motion a bit better. So also another thing is that if you're trying to find the final velocity it has, then, which I put down here, then you would find the final Y velocity, and then the initial and final X velocity is just going to be the same. So the initial, so the Vx here is just going to be the same Vx here. And you can just use this to find, you can use Pythagorean theorem to find the V final. And another thing is that the theta, the initial theta will always be the same at the end. So this theta will also be equal to the initial theta, but just negative theta. So the final theta is equal to negative initial theta. Another thing to notice is that the gravity, which is the acceleration of gravity, which is the A the entire time, is going to have to be negative for this coordinate system. So, and it only acts in the Y direction because there's no gravity in the X direction. So it's going to always be acting downwards, which is going to be negative G for this coordinate system. So it's important to notice that depending on the coordinate system you use, which is very important for these kind of questions, A could be negative G or G, but in this coordinate system where Y is pointing upwards, it's going to be negative G for the Y. Okay, so now I'll talk about the equations that you have for projectile motion. So you have horizontal distance, horizontal velocity, vertical distance, and vertical velocity. So if we get that projectile back again like this, then we know that the Vx, also this is for a ground level projectile. So we're assuming that this is 0 and stuff like that, and it ends also at 0. These are both 0. So Vx, actually I'll start with this equation. So the final position, which is this position, is equal to the initial position, which is this position, plus Vxt. And since there's no acceleration acting in the X direction, it's just gonna be this formula. And you can also write that as xf equals xi plus v initial times cosine theta times t. So this is your first equation you have. And then your next equation in the x component would be vfx is equal to the v initial x. And then since, again, there's no gravity, there's to be just this. And this is another way to prove how the velocity is just going to be the same. So another thing is the y component now. So for the y component, the y component, you would write the same equations. So the final y is equal to the initial y, and then plus initial y plus v yt, dyt. And then now, because I chose this coordinate system, it would be plus 1/2 negative gt squared, or just negative 1/2 gt squared. You can write that as well. And so this would just be v sine theta. So it would be yf equals y initial plus v sine theta t minus 1/2 gt squared. And you might notice as well that the final y position and the initial y position are both, if we're assuming that this is the origin and this is at 0, that both positions are at 0. So this would be 0 and the height would still be 0. So you might be wondering how to find the height. So to find the height, it would just be, the max height would just be at this point. So this is the halfway point, and you would assume that you just like your y projection would be in that here. So it would be y max, which would be this point, equals the y initial, which is at this point, plus v y t, and then still 1/2 minus 1/2 gt squared. But just remember that the time needs to only be the time it takes to get to here. Okay, so these are the equations you have for projectile motions. So now I will give you guys an example, I think. So this example is for projectile motion. So a driver on a motorcycle speeds horizontally off a 50-meter high cliff. How fast must the motorcycle view the cliff if it is to land on level ground below 90 meters from the base of the cliff? So your projectiles aren't always going to be from ground level like this. It sometimes might be, it sometimes might be like on a cliff like, okay, I'd rather click better. So on a cliff like this, and then it lands on some point here. So it tells us that the cliff is 50 meters high. So height is equal to 50 meters. It's 50 meters, not 500. So if your motorcycle is like this, I don't know, and then it drives horizontally at a horizontal speed off the cliff, that means it's only going to go this way and then it's going to drop down like this. So you can see that there's no y component for the initial velocity. It's unlike if it's a different situation where it was like this, where it got shot off at an angle like this, and then like that, it would have the y component and x component. But since it's speeding horizontally off a cliff, there's only x component initially. So it speeds horizontally off a cliff. How fast must the cliff leave to land 90 meters below, like from the base? So how far must it go to land? How fast must it go initially to land 90 meters away? So in this question, you would need to find the velocity in the x direction initially. So there's the diagram for you that you can use. And you guys will have, I'll give you like 4 or 5 minutes or 3 minutes just to go this question. And if you have any questions or a solution, just message it to me again. All right, so I'll give you 4 minutes, I guess. An important thing to know is that you always have to write your coordinate out. So your coordinate system out. So you could write your coordinate system like here. So this is your initial point. This is x positive y. Or it could be something like this is your initial point or something like that. So you would start at a different initial height. That makes sense. Uh, so I'll let you guys have a few minutes. Okay, so I'll just explain it now. So in this question, yeah, you're asked to find the velocity to get this distance. So your initial velocity is just equal to your horizontal velocity. So you know that already that. So I'm gonna put my coordinate system starting here. So this would be the origin, and this is x positive, y positive. So since y positive is going upwards, then the a would actually be negative g. So my final height would just be 0 since it goes all the way down here. Is equal to the initial height, which is h. And then since there's no y velocity, it would just be plus 0 and then minus 1/2 gt squared. So you could write it as the negative h is equal to -1/2 gt squared. And then h is just equal to 1/2 gt squared. So time would be equal to root 2h over g. So that's the time you have. And I'm not going to plug anything in yet. I'll plug it in at the very end. So since that's your time, now you want to use like your x equations. So you would have your final x, which is 90 meters, is equal to your initial x. Since my coordinates is up here, the initial x could be at 0. So this would be 0. And then plus v. It's not going to be v cosine theta this time because I'm starting off horizontally. And that's my initial velocity. So there's no component in that. So it's just v initial times t. And then that's it. So since this is 0, it would cross it out. It'd be d is equal to v initial times time, which we plug into here. So root 2h, root 2h over g. So now we can plug in to find v. So the d we know is 90 meters, and then is equal to v times root 2 times 50 over g, which is, I'm going to assume you guys know that g is equal to 9.8 meters per second. So around 9.8 meters per second. So then v, you just divide that, it would be equal to 28.2 meters. So you guys can check this work and message me if you don't understand it. So that's it. Okay, so I'll just move on then. Okay, so now we have, so we're starting now at ground level. So this is going to be my y coordinate, this is my x coordinate. So this is x, this is y. So now we're going to try deriving the max range that a projectile can have, the max height it gets, which is out here, this is the max range, and the total time it takes for the projectile. So for this question, we already know that since this is where we're launching at v initial, that the x is equal to v initial cosine theta, vy is equal to v initial sine theta. So to find max range first, range has to do with the x component. So the range, what are known as r, is equal to, since but this is my coordinate system, it starts at 0, then plus v cosine theta t times t, and then that's it. So to find the max range, we need to know the time. So we can find time by using the y instead. So vy, oh, sorry, y final is equal to y initial plus v sine theta t, and then minus 1/2 gt squared. So we know this equation already. So v yf is equal to 0, y initial is equal to 0. So 0 is equal to v sine theta t minus 1/2 gt squared. So now we can find out that negative v sine theta. If we move the v sine theta to the other side, v sine theta t is equal to negative 1/2 gt squared. So cancel the negatives and cancel one of the times. So now we have v sine theta is equal to 1/2 gt. And if we solve for t, would be equal to 2v sine theta over g. So while trying to derive the max range, we've already found the total time for the projectile to take. So this is the total time. This is the total time. So now if we go back to our equation for our x, which is r equals v cosine theta t, now we can just plug the t in. So r is equal to v cosine theta times 2v theta, 2v sine theta over t. Okay, and then we can write as 2v squared sine theta cosine theta over t. So you guys might have taken trig already, but 2 sine theta times cosine theta, you can write that as v squared sine 2 theta. So this sine 2 theta is equal to 2v sine theta cosine theta as well. It's just the same thing. Oh, okay, so and then divided by time. Wait, hold on, that right. Wait, hold on, sorry. It's over g, sorry. So it's not time, it's g. So then this is g, this is g, and this is g. So over g and then over g. So the range for a projectile would be v squared sine 2 theta over g. So a good way to check if you're, a good way to check for example, if I want to find the max range for any kind of projectile, then what would the angle have to be? So the angle would have to be 45 degrees, because sine 2 theta, when it's 45 degrees, it would just be sine 90, which is just 1. So, and then r would be equal to v squared over g. So you find the max range possible for any projectile if the angle is 45 degrees. And you can also check extreme cases. So if theta was 0, then this range would just be 0 as well. Okay, so now I'll find the max height. So like I said when I was explaining it in the beginning, the max height would be at this height, and you can't take the entire thing because then it'd just be 0. So if we take it at the midpoint, then the time, since we don't even know the time is from back here, we know that the time is 2v sine theta over g. So time is 2v sine theta over g. So halfway, it would just be v sine theta over g. So the time to get to the half point is t half, this is t total, is equal to v sine theta over g. So now we come out a right equation. So y final, which is just, let's say h is equal to 0, because we're starting at the origin, 0 plus v sine theta times t minus 1/2 gt squared. So now if you want, you can plug that in and you get h equals v sine theta times v sine theta g over g minus 1/2 g, and then t squared would just be v squared sine squared theta over g squared. So now you can start canceling out some stuff. So g, so that's 1g gone. So you get h is equal to v squared sine squared theta over g, because if you multiply this and that, and then minus 1/2. So v squared sine squared theta over 2g. So that would just be equal to v squared sine squared theta over 2g as well. So the max height is equal to this. So you would probably find the max height of anything if theta was equal to 90 degrees, which is makes sense because if you're pointing it straight up, then it would go obviously the max height compared to like shooting it like this. So these equations, I'll write them out again. So the max range is equal to v squared sine 2 theta over g. The total time is equal to v 2v sine theta over g, and then the max height is equal to v squared sine squared theta, sine squared theta over 2g. So these are the equations you get when you divide them. Okay, so now we'll do something. We'll do some questions about projectile motion now. Okay, so let's say that this question first. So in this kind of question, you're given that that's a bad drawing. So a ball is being dropped and another ball is being thrown off like this. So going like that. So the question is, do they land at the same time? The answer would actually be yes, because I'm going to assume you guys know free fall from, I think, the first Physics Club lecture. So for this, okay, let's write the equation for both balls. So for the ball that's being dropped, it would be, so I'm gonna make it, again, this my starting coordinate point. So this is my origin. So it's being dropped at 0. So, oh no, it's being dropped at this height. So this height is equal to, since it lands at this 0, so this is 0. And since it's being dropped, there's no velocity. So it's just minus 1/2 gt squared. So we already know that h is equal to negative 1/2 gt squared. And then for the projectile motion, we know that for the y component, it's h as well. It starts at 8. Oh no, sorry, it ends equals, oh, hold on, I think I wrote this question. Sorry. So it ends, the final height is 0 and it starts at h and then minus 1 pt squared. So then when you move this to the other side, it's negative h and then negative 1 pt squared. So it'd be h equals 1/2 gt squared, sorry. And then for, again, the projectile motion, it would be 0 is equal to h, which is the starting point. And since it's being thrown horizontally, like the other example I had, it doesn't have an initial y velocity. So it'd be plus 0 as well, and then also minus 1/2 gt squared. So you get this is also h is equal to 1/2 gt squared. So you can see that these two equations are the exact same. So since they both have the same height and the g is constant, the time is equal to the same when they both land at here. So that's that question. And I think I have time to explain this final question right here. So this is the following object problem. So as you can see in this diagram, a projectile is being shot like this. And then there's a can. Let's say, okay, don't worry about that mouse right there. The can is being dropped. At the same time, the bullet is being projected. So if this projectile is going like this, for example, I think this is the wall. Where would you have to shoot it in order for it to land at the same place? So for the bullet would have to hit the can as well. So would you have to shoot it above where it's supposed to be at the can? Okay, let's say the can's like right here. So would you have to shoot above the can, at the can, or below the can? So the can would actually you would actually have to shoot it at the can, because if you draw it out, so I'll do all these weird lines. So you have to shoot it like at the can, because at 0G in this picture, you can see that it would only hit it if it was at the can. But since there's gravity now, it would be a projectile motion like this, and then the can would fall like that. So we can write the equation to actually prove this. So for first of all, we know that this is some kind of length and this is some kind of height. And then we know that this is shot with initial velocity, and then this is v cosine theta and v sine theta. So we would write the equation for, let's say let's write the bullet first. So for the bullet, this is for bullet. It would be equal to, for the x, first of all, it'd be equal to L is equal to 0 plus v cosine theta. And then for the y, it would be equal to some kind of, like, since it doesn't meet, it meets at some random height. Let's say this is, I don't know, d. So d is equal to 0 plus v sine theta minus 1/2 gt squared. And then, so for the can now, there's no, since it's being dropped, there's no x component, so just be 0, then y would be equal to, it's in free fall as well. So let's say it starts at h, so d equals h. It's being dropped, so no velocity, minus 1/2 gt squared. So we already know that, for example, the tangent theta right here in this entire place would just be equal to opposite over adjacent, so h over L. And we also know that this other, it's also equal to Vy over Vx. So we can write this now as, first of all, oh shoot, sorry. This is equal to, this is times t as well. This is V, these are all, this is V sine theta times t. So we can write t is equal to L over V cosine theta. So now if you plug it into d, it'd be d is equal to, d is equal to V sine theta over L V cosine theta minus 1/2 g times L squared over V squared cosine squared theta. Oh, I don't know, space. So d is equal to V and V cancel out. So sine theta over cosine theta is just tangent theta times L, and then minus L squared G over 2V squared cosine squared theta. And then for this equation, be d is equal to h. H as well is equal to, since h is equal to L times tangent theta, we can just write h as L times tangent theta. And then if we plug this in, minus 1/2 gt squared, you would get this as well. So you can see that the distances would be equal when the gun is aiming at the can. Okay, so I'll see you guys next week. Actually, I won't see you guys next week, but have a great weekend. All right, see you guys later.